Advanced Financial Modeling, Topic 4, VaR, Value at Risk, Time Value of Money Functions, and Multi-Period Portfolio Modeling using Excel and VBA macros. Some references from the Benninga textbook, if you're interested or want to learn more, is Chapter 1, Basic Financial Calculations, and then there's also topics in Chapters 24 and 25 on generating random numbers and Monte Carlo methods, and also in 26, simulating stock prices, and 28 and 38. So, learning objective number 1, we are going to calculate portfolio VaR, or value at risk. So let's talk about this concept of value at risk, or simply just called VaR. VaR is probably one of the most used risk measures in finance for a portfolio. One way to interpret VaR is it's the most you should expect to lose given a certain confidence interval over a specified period of time. So it's easier if I just give you a VaR, a sample of a VaR, and we can talk what it means. What if someone told you that your portfolio's 95% confidence interval 1-year VaR, written like this, is $27,900. 95% 1-year VaR. What that means is you're 95% confident that losses will not exceed that VaR amount, $27,900. But also means there's a 5% chance or probability of losing $27,900 or more. One way of thinking about it, it's a one-tail statistic. Say your portfolio value is, say, has a mean value here, and someone says the VaR is 27,900 for 95% confidence interval. What you're saying is that there is a 5% chance of losing 27,900 or more, and a 95% chance that losses will not exceed that value of $27,900. So it's a one-tailed distribution critical value. Now, if you assume that asset returns are normally distributed with mean mu and standard deviation sigma, then the X% confidence interval VaR for portfolio is given using this formula. So we'll say that the X% 1-year VaR is going to be equal to minus the V, that's the current portfolio value, times the annualized mean minus Z of X times the annualized standard deviation. So let's talk about this Z of X. All right, Z of X is the critical Z value associated with that confidence interval. So for example, say your portfolio value today is $100,000. You're looking for the 95% confidence interval VaR. So Z of X, using Excel's norm S inverse function of 0.95, gives you a value of 1.65, or more precisely 1.645. So what that's telling you is when I plug in this formula, Z of X is 1.65 or 1.645. So we can just write this formula out, minus V, $100,000, times the expected return, 5%, minus 1.645 times the volatility. So the 1.645 just comes from the geometry of the normal distribution curve. I should expect only a 5% chance of having a 1.64 standard deviation tail event in one direction. So what that's telling you, if you can kind of think about this formula here, is my current value of the portfolio is $100,000. It's expected to grow by 5%, so I'm expected to go to 105, but there's a 5% chance it could be 1.645 standard deviations lower than expected. So that's how you can interpret this VaR formula. I expect $105,000, but there's a 5% chance that I have a 1.645 standard deviation below the expected value. So you can see the calculation here is 27,900. Now this negative sign is really just to change the sign. The VaR is a loss concept. It gives a loss value. So it is, in theory, negative 27,900. But VaR, everyone knows it's a loss value, so you just quote it as a positive number. So that negative sign just flips it to make it positive. All right, so that's the VaR formula. Now, Given that VaR formula for annualized VaR, we could also calculate a daily VaR by just substituting daily means and daily volatilities. All right, so if I want the, say, T-day daily VaR, so say 1, 2, 3, 5, 10 days, I would take the same formula, except I'd use the daily mean times the number of days minus z of x times the daily standard deviation times the square root of time. So if you're looking for the 3-day VaR, that would be the daily mean times 3 times that z value times the daily standard deviation times the square root of 3. However, I usually would use this formula here, the more general formula, because in finance, most return and volatility measures you have are annualized. So if you're looking for the T-day VaR for X confidence interval, and you're given annualized means and annualized volatilities of the portfolio, what you do is just take the annualized mean divided by 252, that turns it into a daily mean, and take the annualized volatility divided by the square root of time, or 252 days in a year, that turns it into a daily standard deviation, and then multiply times the square root of t, which again, if you're looking for a 3-day VaR, this would just be 3 days, and this would be 3 days. So there you go. It's a little discussion of that z value. The most common VaRs are 99% confidence interval and 95% confidence interval. So, and the one we've been using so far is a 95% confidence interval, and that critical z value, the number of standard deviations away from the mean, is 1.645. If you're using a 99% confidence interval, actually it's probably out here a little bit more, that z of 99%, that norm S inverse, is 2.326 standard deviations. So there's only a 1% chance of having a 2.326 standard deviation away from the mean in one direction. And if you're using a 90% confidence interval, the z of 90% is 1.28 standard deviations. So in general, these are the only VaRs I've actually ever seen published, and mostly they're the 95% and 99% confidence interval VaRs. So just to rehash the concept, if someone says the 99% confidence interval 1-year VaR is $27,900, what that means, there's only a 1% chance of losing more than that amount, or you're 99% confident that losses will not exceed that VaR value. So we'll just go to a spreadsheet and we'll enter in the VaR formula, and we're going to use that last formula. So I'm going to jump to the spreadsheet and enter this formula. To make life easier, I've already set cell range names. So if you look up here in the corner here, notice I've given this portfolio value in B2 a range name of V. The annualized mean, 5%, I called it UA for mean annualized. The annualized vol is SA. T is the number of days, 252. That would be, say, if I want a 252-day VaR. And the confidence interval, I just gave it a X. And you can see the Z value here is, I did a formula norm S inverse and then of X, and that gives me that 1.645 we talked about before. So if I want to do the VaR formula, I can just use my range names now. I'm going to start off with a minus V, which is B2, times, open bracket, the annualized mean divided by 252 days in a year. That'll give me the daily mean, times T, which is the number, the VaR's parameter of how many days you're looking for the loss value, minus Z times the annualized standard deviation, SA, divided by the square root of 252. That turns that annualized volatility into a daily volatility, and then I'll multiply that times the square root of T, and there's my $27,897, rounded up $27,900. So this is the general formula. Now, if you want to know how much can I lose in one day, I would just change this parameter to 1. And I would say I have a 5% chance of losing $2,000 or more on this $100,000 portfolio. If I want to know a 5-day VaR, there's a 5% chance of losing 4,500 or more. I can change this to 99%. And you can see over the next 5 days, there is a 1% chance of losing 6,455 or more, assuming that returns are normally distributed with an annualized mean of 5 and the volatility of 20%. So that's how I calculate VaR. Some limitations to the VaR. Well, first of all, the best thing about VaR is it summarizes an entire portfolio in one number. Here are its limitations. Generally, it assumes normal distributions. So in general, VaR is often calculated in the way I just did it in the last few slides and in the spreadsheet, and assumes a normal distribution. The problem with that is asset returns tend to have a normal distribution, but they tend to have much fatter tails. So VaR is probably underestimating the risks of the portfolio. Well, for example, there's a 1% chance of a 2.33 standard deviation change, assuming normal distributions, just based on the geometry of the normal distribution curve. However, October 29th, 1987, there was a 21 standard deviation change in the S&P 500 that day. Assuming there was about a 1% daily standard deviation if you calculate the annual, the historical volatility. So on that day, there was about a 21 standard deviation change. That should only happen about once in every, I forget the number, about 11 billion years or so. And I guess those events do happen, but we've had big changes in the market, which, according to normal distributions, shouldn't be occurring as frequently as they do. The other problem with VaR is it's a static portfolio measure. The assets are fixed, the weights are fixed. So over a period of time, you might be changing your portfolio, especially if you're looking for a 1-year VaR. Also, it's a single period. What I might be asking for, some more interesting problems in portfolio risk is I'm saving for my retirement. What are the chances I won't have enough money in 50 years or 30 years? So VaR is a very interesting, valuable metric, but it's got some downfalls. So what we're going to do in the next topic is start to construct multi-period portfolio models, and then use those to construct risk measures.